Applet here in a second, and we'll look at some pictures. It'll be beautiful. But let me give you kind of a general idea of where we're going with this. The general technique in finding a volume of anything that's kind of non-standard. I mean, thinking back to the very first time you calculated area by hand of your hand. You remember that? Yeah. I mean, you kind of use approximation techniques. This is like the king of calculus right now, right? You use approximation techniques and then you make them better, right? So in the case of volumes, instead of dividing into thin strips in the plane, we're going to divide into thin slabs, right? In space, in three-dimensional space. So this will be the method, right? We'll cut up our solid into pieces. See if we can come up with some formula for the cross-sectional area of each piece. And then if we can get that in terms of x as we move along the x-axis or something, and then we'll just integrate. We'll add up all those cross-sectional areas. In fact, I think the very first time we encountered integrals, I had you calculate the volume of a football or something like that. It was on that exploration worksheet. You remember? I don't know if you even recognize that that's what was happening, but you were actually doing some of this right then. I think we gave you a graph of the cross-sectional areas of a football, and you summed it and you got a volume. So it's actually maybe something you've thought about a little bit before. I don't know. So each of those slabs, in our case today, will be cylinders. We're going to do things that are volumes. We can do this apply this technique to all sorts of volumes, but the ones of interest today are ones that when we take the cross-sectional area, we get circles, okay, in particular. So they'll all be, these slabs that we're talking about will really be like infinitely thin in height cylinders, right? And here's a picture of an approximation to the volume of this solid, right? You can see even the Riemann style slabs that we're producing, right? Each of those cylinders, this maybe we don't know how to calculate the volume of, but these each individually we do know how to take the volume of, right? So, and if we can systematize that approximation, then we know how to take the limit then, and that's the approach we take. So now let me freeze this. I'll pull up this applet. I just want to show you the kind of pictures we can get with this. I can show you this slide again in a second, but let me just take you to this apple for a second, which you can go to on your own time too. So I graphed, for example, the following function using this applet. The reason I'm using this applet is because it allows you to visualize this solid really nicely. And I tried to pick one. Actually, I don't know what that picture was in our. I could actually probably try to approximate. I don't know what we think that is. Doesn't matter. Whatever. This looks something like it. This is the general idea here. So I picked 5 sine of x over 3. Whatever. Okay, so it's some sine. It's like one arc of a sine wave. And then the thing we're about to do today is to picture this in 3 dimensions here. Okay. And we're going to rotate this around the x-axis. Are you ready? It's exciting, I know. I haven't done all the way. I just wanted to pause to let you see what's happening here. Okay, I'll resume. Do you see the figure that's being constructed right now? And actually, I think, can I do, make it solid? You can change the color. This thing is awesome. What color do you like? Salmon? Oh, this is the other color. Here, salmon. Cyan on the outside, that doesn't look good. red and salmon. There you go. Well, now you can't see the inside. Yeah. Here, I'll wireframe again. But can you picture the thing we just did? You can still see the curve there, and you can see what. I just want to make sure you have a visual on this. Okay. We'll also try to maybe practice learning how to draw them by hand. Okay. This will be art class. Anyway, somehow it calculated the volume of this, by the way, by some hidden means that we have yet to find out this period. Okay. So, but anyway, you can have this do all sorts of figures, and this is just the first of many. So anything like this, where a solid generated in this manner, we might call a volume of revolution. Okay. When we take the limit of this kind of approximation, of course we have in the limit an integral again, right, as usual, where the integrand is the cross-sectional area at a given x value, right? So this is a general technique, but for cylinders, I want you to think about what would the cross-sectional area be if it's always a circle. How would we calculate that? For a given x value, we have the height of the function. So what does that correspond geometrically? Yeah, I think it's the radius. By the way, I have brought some, here's the math toys. I'll pass these around now and you can play with them. I feel like you've probably seen this kind of thing before at a party store, or hanging in the grocery store or something during Valentine's Day or something. Right? But you see how this is a volume of solid generated by this process, by a revolution around its central axis. Yeah, there you go, pass it around. I brought some other ones that are less high quality. Let's see. There's a bell thing. Isn't that cute? I think you can latch it and then actually make it a decoration. You can pass that around too. What is this? I don't know. That is not worth passing around. Okay. Theoretically, it should be like a dome of some kind, though. But it's kind of past its prime. Okay. This is a kaleidoscope. I don't know. It's not really that interesting, but it's also got that kind of symmetry, right? The fact that it's a kaleidoscope has nothing to do with what we're talking about. That's it. Okay. This is interesting too. Be careful with this one. It's got like tape that's holding it together, but this does nicely visualize the kind of thing we're doing right now, right? You can take a look at that. If you're not careful, this thing comes out though. Like I just did. So just be careful. I'll pull this thing down. Also, here, let's throw this down here. Here, just be careful with it. Okay. But you can kind of visualize, see how you might calculate the volume of one of these solids. So we'll make this more tangible here by actually giving you an example. As usual, we've got to give you an example. We'll start with a potato. So I actually took a potato and I took one end of it and I laid it on top of graph paper really carefully. And I did an interpolation on the points, and it was beautiful. The thing I got was exactly, remarkably, this function, y equals root x. It was like perfect. This is a perfect potato. Okay. So let's actually do this. I think the picture we're going to get is down here, right? If we take this on the interval 0 to 4 and rotate this around the x-axis, this is the picture we'll get. And let's actually find the volume of this thing. So this is the technique we're going to use, right? We're going to cut this into pieces and think about each piece. Someone already said a second ago, how do we calculate this region, the area of this circle? Well, I think everyone knows the area of a circle is pi r squared. So that's cool. I think I know how to calculate that if someone comes to me with the radius. And what is the radius here? And it's simply just the height here, and marked up here, right? Which is just simply the function that we're given, right? So if this is a cylinder here, then pi r squared times the thickness. And by the thickness, what do we mean here? If this is x moving across, then what are we going to call the thickness? Yeah, we're thinking of it as being very small, delta x, or in the limit, dx, right? So it's got this dx thickness, and its cross-sectional area is pi r squared. But of course, r, we just said, is just the y value of our function. So far, so good. And the thickness, we just said, was dx. So I think we already have a program set out for us, don't we? We have this, and we're just going to slap an integral on it and integrate from something to something. From 0 to 4, we want to add up all such volumes, or all such cross-sectional areas times dx. So integrating from 0 to 4, and will give us our result. In a minute here, we'll have an exact answer. I think you'll actually appreciate the fact that the square root of x, which might seem like a terrible function to start with, actually is a perfectly wonderful function to start with, because what happens here? Perfect. We're just integrating. The pi can come out, if you like, of the integral, and we're really just integrating x. Wonderful first example, actually, yes. So in a second, we're going to have a volume, because I think we all know how to integrate that by hand even, from 0 to 4. So we get a volume for this of exactly 8 pi. I could type this into that program. Would you want to see us do that? It would be fun. Let's do that. Spin it around. See if it gives us 8 pi as well. I don't know what 8 pi is. 25? Something like that. Okay. Okay, any color requests? Purple. I love it. Okay. Do we add purple? How about lavender? Okay. Pause. You seeing this thing being made? Right now this is just a wireframe here, right? Alright, continue. Oops. Yeah, there we go. What did it get for the volume? People in the front row can see. 25.13. Is that 8 pi? Probably. You can check on a calculator. Good. So we've now seen it with our own eyes. It's beautiful. Okay. Are there questions about this process so far? We good on that? We'd like to also obviously mess with you in other ways too. So we'll also rotate around other axes maybe too, right? Can we do this around the line y equals 1? How would that look? How would we go in that direction? Well, again, I want you to always kind of sketch pictures here, do some geometry, like actually think about the measurements you're going to take. There's no substitute for a picture on these. In fact, I mean, how would you draw these kinds of things? I might just start by drawing the region, because some of you are right now even in your notes trying to do this, so I want to make sure you're like doing this correctly. You might copy the region down below, a reflection over the x-axis as best you can. And then maybe at points not on the x-axis, you create an ellipse through those points. And in some sense, we're almost already done, right? I mean, that already looks decent. If you want to add for some other points and their reflection, other ellipses, you could get some dimension to it or something, you know? If you want, you could kind of, I don't know, some of you might like to be more artistic about it too. You could like have that send, but maybe you just want like one side of it, kind of. And maybe you want to add like some of this too, some of that wire frame, right? Maybe you want to add some shading, you know, whatever. Make that thing look pretty, you know. Convince yourself of what this looks like. Looks like a ham, yes it does. It's true. Maybe like a reflective spot on it that's like making that thing shine, or whatever. You can do whatever you want to make this thing. This is the artistic part of your calculus course, so like this is your chance, right, to express yourself, okay? But I do think that a good picture goes like a long way to solving any of the problems that we're going to encounter in this year. There are a bunch of other kinds of volumes we'll encounter, and in all cases, it'll be really helpful to visualize correctly the region and then the volume that's being generated. So again, let's make sure we're clear. If we're rotating the same region around y equals 1, then this is the radius, isn't it? And I could do this in the applet in a minute too. We can go back and have it rotate around a different line. Well, then what function are we really thinking about here? Like, what is the radius now? It's not root x. It's what? Yeah, it's just root x minus 1. And no one had to tell you a formula there. Okay, well, if you're rotating around like y equals 1, you need to do f of x minus 1. It just makes sense geometrically, right? What would it be if it was y equals negative 1? Yeah, it'd be root x plus 1. Okay. What if it was y equals 2? Which is it? I mean, now we're calculating this distance, right? So 2 minus root x, right? I mean, isn't that how you do it? You take, okay, well, this distance is 2. This distance is root x. For any given x value, that's root x. So we do 2 minus that root x. So I just want to make sure, and did I just give you any formulas? Well, not really. We just thought about the picture, right? We're just thinking. So that's what I'm trying to say about the picture here. So yeah, I think the radius in this case will be root x minus 1. And now this is a little bit more problematic to do by hand. It's still possible, though. You could expand this out, and it would only be stuff that you could integrate. You could integrate that by hand, but I'll just tell you. You can actually integrate. Again, in fact, there will be questions, especially in the calculator portion of our test at the end of this unit. There'll be questions that ask you on the calculator portion for this kind of work. And the only thing we're expecting on the calculator portion of this is for you to correctly write down this and then give us an answer. There's like 4 points maybe associated with getting the correct boundaries, setting up the integral correctly, lots of points associated with just writing down the correct expression. And then like 1 point for going from there to here. Right? So don't, just to be clear, I mean, that's the kind of thing we're emphasizing in this unit, even though obviously like the warm-up today, I'd still like you to do these things by hand too. So maybe I'll show you this one here too. I'll show you this one while you get started on this one here. Let me freeze here. We'll do this one here in a minute, but we're going around this time around the y-axis, right? So is that an okay thing to do? Yeah, hopefully. We'll do that in a second. You can start thinking about it. What was the previous? Okay, so same function but around y equals 1. Okay, I'm already ready actually. Oh, did we, on the last one, did we go from 0 still? Oh, here. We went from 1, since that was the intersection, right? Otherwise, it doesn't make sense otherwise. So from 1 to 4. All right, so we'll come back to this problem in just a second. I just want to show you the picture of the last one. So here's that region just from 1 to 4. What did we get as an answer? 3.6 something? So is that the shape you expected to see? 3.665, right? We're actually not in this course of study going to talk about how to compute the surface area. So bonus for you if you want to look into that. It's completely doable, but it's just beyond the scope. It's just not in the BC Calc curriculum. All right, so yeah, we're ready to do around the y-axis. I think this harkens back to what we did yesterday, right? Like for the very first time, I think yesterday we were integrating with respect to y. Well, that's going to happen again. You can already maybe picture where this is going. Our cross-sectional cylinders will be perpendicular to the y-axis this time instead of the x-axis. Not a problem though, right? But calculus works with any letter. So this is the picture we're getting of root 1 over root y. If you prefer to, just for the sake of sketching it, to draw the graph of y equals 1 over x squared for positive values, that would work too. If you prefer to see it that way and process it that way. But there's no reason that you as a mature mathematician can't just like think through how to graph x equals 1 over root y, right? Choose various y values and output x values. It's not a problem. So the point is, do we have a very clear picture in our mind of this? I mean, I kind of gave it to you. I should have maybe let you sketch this region first. But is this clear that this is the region we're talking about? I hope so. This is this boundary. It says let's restrict y from 1 to 4, so that's, I guess, what we're talking about. And then it says also, and the y-axis. So now we have kind of 4 boundaries that were given in the problem that define this region. So I think it's very clear what region we're talking about. And now we want to revolve it around the y-axis. So we get that kind of a picture, right? And then again, like we said, these are going to be horizontal discs with thickness dy. That's nice. The function I already gave you is actually in this form, right? It's already solved for y, so there's no work to be done there. So the volume of each slab will be pi r squared. In this case, what is r? Well, just this. Again, it's going to be a favor to you, I think, that we have 1 over root y there, huh? For any given point on that curve, it's the x value, this is what this is saying, that defines the radius, doesn't it? Instead of the y value. So what is this integral to do? And the fact that there's like y's in there shouldn't threaten me. We do need the integral of 1 over y though, I guess, huh?
So is this function, is it like unsolvable in terms of x?
I think you could, I mean, I don't know that you can set up this region if you think about it in terms of, well, I shouldn't say that. We will have another technique, but it won't be this technique for another approach to this. But yeah, so I hope you appreciate from yesterday why here we don't really have, like we might need to just suck it up and do it in terms of y, right? Like we don't have as much of an option. One thing you could do is just like rename everything in this problem that's a y and x. And then, this is certainly equivalent to asking, could you please rotate y equals 1 over root x, and 1 is less than or equal to x is less than or equal to 4, and the x-axis, around the x-axis, right? So that would be actually equivalent, obviously. But I do want you to like become comfortable with thinking flexibly about your letters and your orientation of a picture. What's the integral of 1 over y? Just to remind ourselves. Love that we have a natural log entering into this. This makes me happy. ln1 is a thing I know. ln1 is 0. So we get pi times ln4, right? Or if you want to write this way because you're fancy, you can write that way. If I were accepting your answer on a test, obviously like pi times ln4 would be fine. Just know as usual that like this might appear as a multiple choice answer as 2 pi ln2 or something like that. So I'll give you a chance to process that for a second while I fire this one up. If you want to see, I mean, you can see it kind of there too, but you can check on our answer here too. What was it, 1 over? Oh, actually, I don't know that it lets me do around this particular applet doesn't let me go around the y-axis. So shame on you, applet. Okay. I grew up near 3 Mile Island, so this is close to my heart. This is clearly a nuclear cooling tower of some kind, right? There are 3 on 3 Mile Island. Only 2 of them are operational now because of the meltdown in '79 of the one. But so the one you can still actually, if you tour 3 Mile Island just outside of Harrisburg area in Pennsylvania, you can actually, I don't know how I got a tour. I don't know if they like normally give tours or not, but you can actually walk under the tower and look up inside of it. It's beautiful. It's also another geometric thing that if you, I don't know if you've studied hyperbolic surfaces like this before in geometry maybe, but I wish our math department owned one of these. If you find if you get 2 cylinders and you tie strings to them like this, and then you twist them in an opposite direction, then the thing you get is this kind of shape. And in fact, if you are at 3 Mile Island and you look up, am I doing this right? Maybe messing it up, but they all twist, right? And if you look up inside there, and maybe we can find a picture of this, then you actually see nothing but straight iron, whatever it is, steel trusses, right? Like that go the whole way around. This is really cool. You're like, this is a very smooth, curvy thing. Why should it be made only of straight stress? They're all just at an angle though, inside there, you can imagine. It's called a ruled surface, because you can make it out of lines. Anyway, so whatever, I digress. So let's actually do this though, right? So, very similar problem to the last one. Notice here that you can't even really solve this for x, for y very easily, right? You could, using Poisson formula or something. But it'd be messy. Notice that this is an appropriate problem for the use of a calculator. Do the toys get back around here? But feel free to calculate that here. Start nice and easy today. Yeah, so we would maybe call these disks. Some people call this the disk method. If you want to call it that, that would be a fine way to call it too. And I think you can see why. So we'll generate other solids using other methods in the coming days. And you have new power in your life, I hope you see. So did everyone write down the homework? I can go back to that slide if you need to. And that's what you should get for that last problem.
Yeah, okay. I'll stay.